We are moving forward to our next presentation, this time Project Zeocat 3D by Carmen Garijo. Few words about Carmen, who is here and will present her work in person. She accounts with a degree in chemistry from University of La Rioja, Spain, and is working as a researcher for nanotechnology department in LURREDERA, Spain, developing functional materials and being a key participant in optimizing the FSP synthesis technology for developing new specific nanoparticles. Has acted as technical responsible for several collaborating projects, national and international level, mainly dealing with the different industrial applications of nanomaterials. I'm going to invite Carmen to speak to you about the remarkable results from different specific nanomaterials, including Zeocat project, in her work presentation under the title Design and Production of Very Specific Nanocatalysts by FSP Technology.
Okay, thank you, Veronica. Well, as Veronica has already said, I'm going to introduce you today the design and production of very specific nanocatalysts by the FSP technology. I would like to take the chance just to briefly present and introduce you our technological center. LURREDERA Foundation is a non-profit private entity which was created 24 years ago. We work in different activities and strategies, but mainly the ones are the participation and coordination in collaborative projects in different levels, regional, national, and also international. Just to give you some numbers, LURREDERA has worked in around 400 projects. Nowadays, more than 60 projects are ongoing, from which 11 are at international level, and 3 of them we coordinate from LURREDERA. So additional activities, internal research for the technology and product development. We work also with private companies, and also in the creation of a spin-off companies like Tecnan, which is focused on the production and commercialization of nanoproducts at industrial scale. So the 3 main areas of research in LURREDERA are advanced environment, non-metallic materials, and the nanoparticles. I'm going to focus more in this 3rd area in which I work. So LURREDERA has a great expertise in the production of nanomaterials through the FSP, the flame spray pyrolysis technology. Some of the advantages we can get with this technology is that we can design our nanomaterials. We can produce a wide range of materials. Almost all the elements on the periodic table can be used with this technology. Also, we can design and work on different compositions, also different structures. What else? Also, this technology let us to have a control on the the properties of these nanomaterials. For example, we can work on different size ranges. Also, we get high purity and stability, low agglomeration of the particles. And it's also good to mention the scalability up to kilograms hour. In our facility, we have mainly three different equipments. We can work from a small scale, which is 10 grams per hour, to an industrial scale, in which this equipment can work to 1 kilogram per hour. So, okay, as I have mentioned, we can design a wide range of nanomaterials, and these nanomaterials can be used in different sectors. Here I focus on the catalytic application of these materials with some examples. For example, we can use it in the hydrocarbon and CO oxidation, also NO reduction, the photoreduction of CO2, catalyst for lignin conversion also, and for the conversion of methane to aromatics, which is the main reaction in the Zeocat 3D project. Also the biorefinery biodiesel transesterification reactions. So we have mainly, different applications. Here I have included some examples, some interesting examples of two different materials. The first one is a mixed oxide of cerium and zirconium. And I have included also some images just to let you know how the powder looks like, and some characterization, X-ray diffraction, and the TEM images. The interesting thing of this material was the high surface area, and also that we achieve a great homogeneity of the cerium and zirconium mixture, which enhance the catalytic properties. This study was in collaboration with University of Lille. And the other example is a 4-element composition of a nanomaterial, which is a lanthanum iron perovskite, which is doped with 2 additional elements. In this case, this study was focused on comparing 2 techniques, 2 ways of synthesizing this material, the FSP technique and a co-precipitation process. So we saw that it was a better inclusion of these 2 additional elements on the perovskite structure, and also a better catalytic performance. Indeed, this material produced by the FSP technique worked in the reduction reaction, works in a lower temperature, so the reaction occurs sooner. Yes. I forgot to mention that I have included also the DOI for some of the papers that we have written, just to let you the possibility to go more in deep on these studies. Okay, now focusing on the Zeocat 3D project. In this project, we have produced different nanoxide based on molybdenum for the chemical conversion of methane into aromatics. So firstly, we started with a production of simple molybdenum, in which we get estimation of particle size around 100 nanometers. And then we started doping this simple molybdenum, and among the different dopants, we work with firstly iron dopant. With this introduction of iron, in this percentage of 1%, we get a reduction of the particle size, a higher surface area of this material. And there were other options of dopants, for instance, the platinum molybdenum, that in some catalytic tests carried out by the University of Poitiers, we saw that this dopant was better in their catalytic behavior for this reaction. So we finally selected this platinum doped molybdenum nanoxide. So we going more in deep in this composition, we carry out and produce different batches synthesized under different production conditions. So as you can see, there are significant differences both on physicochemical and catalytic properties. And well, here in the image, you can see, well, visually the physicochemical, the appearance that were really different. Also, we get a higher surface area in one of these material, which was the finally selected one, the finally selected, but due to their activation on the catalytic behavior. So this material was more active than the other one. Okay. So now I would like to mention some highlights according to this project. First of all, as I've mentioned, we finally select the platinum molybdenum nanoxide, this dopant, as it has a better performance, a better catalytic performance than the iron doped nanoparticles. Also, Democritus carry out some toxicity tests in which we saw some non-toxic behavior towards lung and prostate models, and also that this composition, this nanomaterial, can be used safe in a safe way, I can say, at concentrations below 200 micrograms per milliliter. So these are some relevant results that we can mention. Okay, apart from the production of nanoparticles in the project has been additional activities that we carry out are how these nanoparticles can be incorporated on the zeolitic supports. And there are 3 different ways. The first one is the traditional molybdenum incorporation, which it doesn't include the nanoparticles, and 2 other options, 2 different routes. The first one is impregnating the zeolite, the 3D printed zeolites through a recirculation setup, and the other route, which is the incorporating the nanoparticles before the 3D printing. So some interesting results concerning the route of impregnating the 3D printed monolith is that there were no significant differences concerning the catalytic behavior. So this stage, or this part of the process of this impregnation doesn't have any influence, or not a significant influence, on the catalytic behavior. Also, we achieve a good distribution of these nanoparticles on the zeolitic support, as we can see on the EDX mapping. We have here that this study has been done by Vito, and also we have the SIM images are for this to know that we get an homogeneous distribution, and also with the EDX mapping, we saw and identified these active materials, the molybdenum and platinum. Okay, so as I have mentioned before, we have 2 different impregnation routes that we work on the project. The first one, just to show you some images, the impregnation of these 3D printed monoliths. The second one is as I mentioned, the impregnation of the zeolitic material in powder before the 3D printing. So in that sense, we have seen that these nanoparticles can be 3D printed, that can be incorporated in the composition in a mix or in a powder and be 3D printed. And also we have worked on upscaling this process, this impregnation process, to achieve and get a more versatile procedure. And we have 2 different approaches. First of all, focusing on the monolith, that we increase the sizes, the dimensions of this monolith, and also that we can work in parallel. So we can impregnate different monoliths at the same time. Okay, I would like now to take the chance to sum up all these highlights and yes, sum up in some in relevant conclusions. To basically highlight the advantages of these nanocatalysts that are synthesized through the FSP equipment based on the technique. Yes, so as I mentioned, we can work and design a wide range of nanoparticles, so we can fix to different requirements. In this case, we finally end up with and select the platinum molybdenum with because of its better catalytic performance compared to the iron. Also, according to additional tests, that we can use this composition, this platinum molybdenum nanoxide in a safe way at low concentrations, as you can see. And okay, also it's important that these nanomaterials can be incorporated in different ways to the support both the different routes of impregnation. And when we 3D printed this mixture, this composition, we do not have a significant a reduction of their catalytic behavior or something like that. Also, it is remarkable the upscalability of the different processes. I mean, not only the impregnation, but also the production process of these nanomaterials with the different equipments that I show you on the initial slides. And well, I think also we also achieve this homogeneous distribution of the materials on the monoliths, which is also very important. And I think that's all from my side. So, if you have any questions?
Thank you very much for your presentation. Let's ask first our audience here in the room if there are any questions. We do have a question from Dr. Alvaro Amiro.
Thank you, Carmen. I really enjoyed your presentation. My question is around the different challenges that the coating of those of the metal on the 3D printed zeolites. Did you make an ink and then you impregnate the zeolites, or have you tried other techniques such as spray coating so you got a core, so you don't reach the core of material?
So I mean, other techniques like spraying the. Yes, no, we basically focus on we design a recirculation setup, basically to let the nanoparticles get inside the holes of the monoliths. We try this methodology, and it seems, as I have seen with the results and in the same CM images from Vito, that we achieve a good homogeneous dispersion on coating on these zeolitic monoliths. But it's also another way to deposit the nanoparticles on these supports. So it's also another route.
Thank you very much. I think we have another question from the audience.
Yes, thank you for the nice talk. I had a question about the particle size, because in many catalytic reactions, the particle size is very important because it has an influence on the selectivity and the conversion and so on. So how controllable is the particle size in your flame spray pyrolysis technology?
Can you repeat? Sorry.
How easily is it to control the particle size with your technology of making these nanoparticles?
Okay, so when we design a production of one nanomaterial, we can work in different stages. First of all, we can work on the preparation of the precursor mixture, in which we study the different possibilities of using one precursor or another, also the concentration, which is an important factor to take into account for reaching one side or another. And there are also additional adjustment on the part on most the technical or when we spray this precursor mixture into the combustion chamber, we can also work on different flows, also pressures that will also have an influence on the particle size. So we firstly do an approach, and when we get the material, the preliminary material, we characterize it, and then we make the optimization, the corresponding optimization and some adjustments, both on the precursor mixer or on the equipment, to achieve the requirements or the desired the desired sizes of the product.
Thank you.
You're welcome.
Thank you. Many questions today. It seems that we have a few minutes for another question.
Okay.
From our side. Could you provide us more details on the different stages of the production process of nanomaterials through FSP technology?
Yes. So basically, it's more in line as the previous question. Well, there are in this FSP technology, we have different stages. So first of all, we study and go more in detail on different ways, on different raw materials that can be used to prepare this precursor mixture. Also, we study the compatibility between the solvents and the precursors, the metallic precursors, that can be organometallic, inorganic, with inorganic nature, or there are different options. So we, in this part, in this initial state, we focus to get an optimum mixture that can be injected on the FSP equipment. We measure calorimetrics, we carry out some preliminary characterization, and also it's important the stability of this mixture. And then in a second step, we focus on the parameters, the technical parameters of the production conditions, paying attention on the flows, also pressure, temperatures, and when we carry out the test, also on how the flame it looks like. I mean, we like to, or it's for to get a good material, or and also with well, how can I say? Yes, it's important that the flame has a good morphology to avoid interruptions, and also some problems of materials staying on the nozzle. So there are different points on which we act. Yes, for this technique.
Thank you very much.
Thank you.
And for your presentation and for answering our questions.
Okay, thank you.
Thank you again.